The problem we would like to look at today is broadly titled quality assurance testing, but really it's about selecting different types of things out of a larger group and then figuring out probabilities under different types of selections. For our problem, we have a case of 12 calculators of which we're going to pull any two. All the calculators look the same, however, we have discovered that 3 of the calculators in that case of 12 were broken and they were mixed in by accident. Now, if 3 were broken, that also means what? That 9 of 12 are good. So, we're going to do this in 3 sets. First, what is the probability that both are broken? A. Both are broken. Well, what we need to do there is get 2 sets of counts. One, how many ways may we select 2 calculators in total? And then second, how many ways will we select out of those 3 broken ones can we select 2? So let's first figure out total ways to select 2 out of 12. And what we want to use there is the combination of 12 items selected 2 at a time. C parentheses 2 comma 12. If you're using a TI calculator, for example, or different types of math books, we'll also express it in this fashion. 12C 2, selecting 2 items from a group of 12. But whichever way you actually do the notation, it always means the same thing, which is n factorial over n minus r factorial, where this is the n, the total number of items being selected, and this is the r, the selecting 2 out of that. So let's try this. C 12(2) is equal to 12 factorial divided by 12 minus 2 factorial times 2 factorial. Let's expand that term a little bit. Factorial, that number times the next number lower times the next number lower, dot, 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 all the way down to times 2 times 1. So this will be 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. This one will be 12 minus 2. That would be 10. So 10 factorial. 10 times 9 times 8 times 7 dot, 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 dot times 2 times 1 times 2 factorial, which is 2 times 1. Now, looking at that, we notice that the 10 factorial, 10 times 9, dot, 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 down to 1, and this part cancel each other out. So what we're left with is 10 factorials canceling, so we have 12 times 11 divided by 2. 2 into 12 goes 6 times 11 is equal to 66. There's a total of 66 ways that we can select 2 out of 12. So to find that the probability that both are broken, that would be the probability that x is equal to 2, both are broken, is going to be how many ways can we select the broken one out of this total of 66 ways. So let's write that up here. We've got the combination. We have 3 broken ones, so the combination of 3 selected 2 at a time. Now, we have broken ones. We also have to select the good ones to make up the rest of the set of 2. Well, in this case, there's none. So this will be times the 9 good ones selected 0 at a time, divided by, from over there, combination 12, 2. Combinations we use when again, to refresh your memory? Think of that before I say it. Order does not matter, and there's no repeats. Okay, 3, 2. We apply this same formula. It's going to be 3 factorial over 3 minus 2 factorial, which is 1. 1 factorial is 1. Divide by 2 factorial. The 2 factorials cancel out, leaving us with 3. Next one, 9, comma 0. This will be 9 factorial over 9 minus 0 factorial, which is 9, times 0 factorial. 0 factorial by definition is 1. 9 factorial divided by 9 factorial is 1. 3 over 1 divided by the 66 that we got previously. 3 and 66, or if we simplify the fraction, 1 in 22. So there's about a 4% chance, 4.5%, 0.0455, that we will select 2 broken ones in a set of 2. Now, what's the probability that none are broken? Let's try that. Probability, part B here, neither broken. In other words, the probability that x is equal to 0. Well, let's use the same process. It's going to be the combination of 3 items of which we want to select none. Combination 3, 0 are broken, times the combination of, we've got 9 good ones of which we want to select 2. All of that divided by that total number, 66, that we can get. Okay, 3, 0, we realize from this any combination with 0 is always going to be 1. 9, combination 2 will be 9 factorial over 9 minus 2 factorial times 2 factorial. 9 minus 2 is 7. The 7 factorials cancel out, so we've got 9 times 8 divided by 2. In other words, 9 times 4. In other words, 36 out of 66. Now, if we'd like to simplify that into the same number of 20 seconds that we have here, divide that by 3, 12, 20 seconds. Or if you're a decimal kind of person, a little over half, 0.5455. Okay, those were interesting enough. Now, let's look at the other possibility here, and that is that one is broken and the other is not. So what do we have here? We have the probability that at least one is broken. So let's write that right here. Probability that 1 is broken. Well, that's the probability that x is equal to 1. But what else? If we just want once the probability that 1 is broken, we have it. If the probability that at least 1 is broken, probability at least 1 is broken, well, then we have something a little different, don't we? We have the probability that 1 is broken, plus we have the probability that both are broken. So one has to be very careful about the wording there. The probability that at least 1 is broken, or the probability that exactly 1 is broken. Could be 2 different answers there. Well, let's take a look at that first part that I put up there. Probability that 1 is broken. That's the probability that x is equal to 1. Now we're going to use the same piece that we did right here. We're going to go, this is going to be equal to the combination, 3 broken ones, select 1, times 9 good ones, select 1, all of those over the combination of 12, comma 2. And what does that give us? 3, combination 1, 3 factorial over 2 factorial times 1 factorial. Answer 3. Combination 9 items selected one at a time. 9 factorial over 9 minus 1 factorial times 1 factorial. So the 8 factorials cancel each other out, leaving us with a grand total of 9. All that over 66. 3 times 9 is 27. 66. And if we want to simplify that into 20 seconds, which is what we were doing based on that first one, divide both sides by 3. 9 20 seconds. Or 0.45. So we've gotten 3 answers there. Here, here, and here. If we wanted to do the question about probability that at least one is broken, we do that by taking how many ways were there that one is broken, 9, 20 seconds, plus the probability that 2 are broken, 9 plus 1 is 10 in 22. Now, when you see that at least 1 in any future problems, you can also think about that as equal to probability at least 1 is broken is 1 minus the probability of none broken. Right? At least 1 is the same as 1 minus the probability of 1. None. Because the probability of none plus the probability of at least 1 is going to be the entire sample space. So here we go, 1 minus. Now, what was the probability that neither was broken? None, 12 and 22. 1 minus 12, 20 seconds equals the 10, 20 seconds that we got in the other part. So it works out. Now, the other interesting thing that we can do with this is we want to double check those numbers. Is it a valid probability model? Is each probability, that is both are broken, neither is broken, or 1 is broken, is each of those probabilities between 0 and 1 inclusive? 1 and 22, yes. 12 and 22, yes. 9 and 22, yes. Second question about being a valid model, do they add up to 1? In 20 seconds, there's 1 plus 12 is 13, plus 9 is 22, so yes, they do. It's an excellent probability model, and there they all are. The other piece that we can do with that is we can actually graph that. And if we said, what's the number that are broken? And that can be 0 or 1 or 2. And what is the probability of breakage? Well, okay, let's do that. How many is our biggest number here? It's right here, 12 out of 22. So let's put the 12 out of 22 up here. We'll make this 6 out of 22, 3 out of 22, and 9 out of 22. So the probabilities of breakage. What's the probability that 0 have been broken? Neither is broken, 12 out of 22. There it is, 12 out of 22. What's the probability that that exactly 1 is broken? It's right here, 9 out of 22. Let's draw the 9 in. This is a probability histogram. The bars touch each other, and they're all of equal width, so it's a good, valid probability histogram. And there we put in the 9 out of 22. And then our last one was 1 out of 22. There's 3, 2, 1. So it's down about here. 1 out of 22. We'll put it in there. And that's our probability histogram for that problem. Quality assurance. We're selecting 2 out of any 12 and trying to figure the probability that that number is broken.